like these to be submitted if you haven't gone over the rules for submission that I put in Canvas. Basically, it's you can if you can't print these out, you can just write the answers. You don't have to copy it and print it and then write right on it. You can just write down the your answers and how you solved them, and on any piece of paper. Now, what I'd like to do is, either you can scan the papers, or you can just, the way I do it, I just take a picture of it with my phone, and then convert those images to like either a JPEG or a PDF or a Word file. It would be really nice if you could get them all in one file. I know a lot of folks just scan them one at a time, and then they get a separate file for each scanned item, and then they just submit all the different files. You can do that, but it's a real pain because then each one of them is a separate thing in Canvas, and it makes it a little more difficult to grade. So I won't take any points off if you don't do that, but it really would be nice if you had them all in one particular file. I can share with you some freeware to do that if you're not sure about how to do that. The way I basically do it is I import them into PowerPoint, and then I basically cut off whatever I don't want to be seen, and then just save it as an Acrobat file, as a PDF file. I think you still have, since you're students at Skyline, I think you have free access to Microsoft Office. I think that's the case. I'll double check on that. But there's also a lot of freeware you can use to do the same thing. So if there's any questions about how to do that, let me know, and I'll try.
Where should we submit it?
When?
Where?
Oh, where? Oh, right on Canvas itself. So you go to Canvas, and just under where it says, this is, what is this? This would be an assignment. Just click right on it, and it'll give you a place to submit your file. So you just save the file, you just say like recitation number 1, and then just submit the file, and you're done.
Because I just clicked on the modules, and then REC FA 20 Intro to Chemistry, and then I didn't see the submission button. So
scroll. Yeah. So you have to click right on it, and it'll give you a place to submit them.
Okay.
And so, yeah, for those working in Apple, I know there's one particular file that people kept trying to send to me. I think it was dot files or dot something. Damn, I can't remember what it is, but it's something for Apple only, and I can't open them. Canvas won't open them. I don't have something that can open it on my computer. So either PDF, Word, PowerPoint, basically any of the JPEG or a GIF. I mean, any of those I can open and read, but the other Macintosh specific files, I can't open them. Okay. So we'll be meeting this time every week, and we'll be basically going through these sorts of problems that are related to the work we're doing. But since like this morning was our very first lecture, a lot of this is going to be brand new. So I mean, basically, we're going to be looking at some of this for the very first time for some of you. So we'll go kind of slow. So what I kind of like to do is, like, maybe I'll do like the first problem with you, and then you can look through and see which ones don't look familiar at all, and we can talk about how to do them. But basically, we're going to sort of work on these together. Not all of them, because I want you to actually do some of the work at home yourselves. But we'll do 3 or 4 of them. So we're not. We probably won't be together for I think we're scheduled for 3 hours, but it won't be that long. Probably 90 minutes, maybe 2, depending if there are a lot of questions. And at the end, I mean, if there's any questions about anything, obviously, since we have this time together, that's we can take advantage of it. Okay. Any questions about submissions or anything else before we get started?
Is there a way we can get probably miss a recitation, or
I missed the middle of that.
Able to? Oh, sorry. 1 second.
You just faded out in the middle. I missed it.
Oh, sorry. I didn't have my earbuds with me. Is there a way we can get the recitation problems if we miss a recitation?
Oh, yeah. There. I mean, it's in Canvas, right under recitations. The very first one will be there, and it's there in PDF form. So you should be able to. Hopefully, you should be able to open. There's enough freeware to open those. If anyone's having a problem opening them, let me know.
Oh.
And I'll.
Oh my bad. I'm tripping out. Thank you.
Format. Yeah. If there's anyone who just joined and doesn't have it, I can put. See, how the hell am I going to?
Someone asks in the chat, is it better to scan it black and white or raw image?
Black and white is fine. I mean, I would recommend you use pen rather than pencil, because pencil doesn't scan particularly well, especially if you don't press particularly hard on the paper. So I would use pen for these. Oh, and a key thing I forgot to mention. A couple key things. So forgettable. I'm not going to grade whether you got the answer right. That's important, right? It's oh my God, I can get it wrong and still get full points. Yes. But 2 things you need to try. I don't care if you get the right answer, because this is all about learning how to do these. If you get the wrong answer, I mean, I get the wrong answer half the time, but you need to show your work. That's essential. That goes for the test too. If you give the answer to a problem, and even if it's the right answer, you're not going to get full marks, because I didn't get to see how you did that. And the key to learning is not getting the right answer, is learning how to ask the question properly. Really, I mean, it's learning how to solve these particular problems in general. It's not getting a specific answer. So if you don't show your full work, you're not going to get full points. So basically, on a test, if it was a 10-point question and you just gave me the answer, you'd get 5. On the other hand, if you showed me all your work and you made one stupid math mistake at the end, this is something I do all the time. It's a tiny bit of dyslexia. So if the answer is 21 and I wrote 12, which I do a lot, you'll get 9 out of 10 points, because I see you knew how to do it. You just made a dumb mistake, and everybody makes dumb mistakes. But you proved that you knew how to do it, which, like I mentioned, is a lot more important than getting the right answer. So always show your work. Even if you screw it up and get it wrong, you're going to get most of the points if your approach was correct. If, on the other hand, you had no idea what you were doing, well, at least you tried. And for this, and for the recitations, it doesn't matter. If you took the wrong approach and took a wrong turn somewhere, you're still going to get all the points, because you saw the question, you tried the question, and you did your best on it. And then what I'll do later is I'll post a key for these. So you'll have these to study for the test. So for tests, I take a lot of the questions out of these recitations, or ones really, really similar. So if you can do these, basically you're going to nail the test. I would also suggest going to Canvas and downloading the text. I'm not going to refer to the textbook a lot, but there are questions at the back of every chapter, and they give you the answer, I think, for either the odd or the even number questions. And so you can go back, you can do them and check your work. And I do steal questions from the textbook quite frequently. So just to be aware of that. And I'll take questions from the textbook and put them into the recitations as well. So it's a good place to go if, like, if my babbling explanation of things doesn't make any sense, and that's going to happen. The textbook is a good place to double check. And it's a good place to get problems to work on, because you get the answers as well. It may not give you precisely how to do the question, but if you get the right answer, you're probably, your method is probably correct. Okay.
So, excuse me?
Yeah. Oh, yeah. There's also a raise your hand button you can use too. So just in case, because I can only see like 4 of you at one time. So I know there's a lot more of you here. So you can use that as well. So yeah, what's your question?
Where did you put the recording on Canvas?
Oh, the recording will go on YouTube. I haven't had a chance to edit it yet. So yeah, so I need to edit it. I normally like chop out the first like couple minutes at the beginning and a couple minutes at the end, and then the whole thing will be put on YouTube. And I'll also, so there's a link to the YouTube page, and I'll put links directly to the lectures and recitations under the lecture slides and recitation section. So I'm normally behind by like a day or two. In the summer, it was really rough because it was just so insanely busy. It won't be, hopefully it won't be as bad this time. So I'll be a little faster in keeping up. So I'll probably post it tomorrow. The lecture this morning and the recitation this afternoon will probably be posted by the weekend. Okay.
Another question.
Sure.
So if we are doing recitations now, and it's due August 24th.
A week, yeah. They're always a week from when the recitations are due a week from when we do them together, and the lab reports are due a week after we do the activity together.
We don't do all the questions yet, right?
Yes, you do all the questions. I'm just saying I'm not going to do them all with you this afternoon. I'll do sort of like, I'll do half of them together with you approximately, and hopefully that'll give you a good enough idea of how to do the rest.
After the recitation, we know some of the answers. Right?
Yeah, I mean, hopefully the ones we do together will be done correctly. I'll try my best, but the rest you do on your own, and then submit the whole thing. Okay. Yeah, so there's absolutely no reason to not get at least half the grade, because hell, we're going to do half the questions right here, if not a little bit more. So yeah, you should get at least that. So the way I think in Canvas, the way I normally said I would grade these is we gave 10 for participation, because when we were together in real life, what I would find is that a lot of like the really good students would help some of the other students work on the questions. In fact, I've spotted a couple of future teachers to be. They were like so good at explaining things. But I mean, since we really can't do that, although I can, at the end of the session, I can just leave this going, and you can get together and talk amongst yourselves and do the questions yourselves. So that's available. So it was like 10 points for actually doing the project, and then 10 points for actually showing up. But what I'm doing now is just basically they're worth 20 points each. And again, I'm not grading to see if they get the correct answer. I'm just grading to see if you did the problem and showed your work for the problem. Okay. All right. And anything else before we get going?
Oh, sorry. One last thing.
Sure. Oh, no. Don't apologize for asking questions. That's the whole point of this.
So our AP Chem teacher back in school was a stickler about organizing questions. He always wanted it to go from like up to down, so rather than like side to side for questions. Do you really care about that, or does
I guess I don't know what you mean by up and down and side to side.
Or like how we organize our answers. Or
no, I mean it's
I guess, do you want it like super organized, or does it not?
Well, super organized is nice, isn't it? But I mean, as long as I can see how you're
Yeah.
doing it. I mean, one thing
Okay.
that I won't be such a stickler for on the recitation, but I will be on test is units. If you give an answer
Oh yeah.
without units in it, I'm gonna get a little pissed off because the number without units is useless. The answer 16 doesn't mean anything. 16 grams means something. 16 liters means something. 16 degrees means something. But so that's one thing. I'm sort of glad you brought that up because that's without units, a number is meaningless in science. It doesn't mean anything. The other thing and that's right here in the very first question, significant figure or sig figs. How many people have gotten that in big red pen on their tests? I'm going to sort of try to explain what significant figures mean because it's really, really important. You may think it's like a minor thing, but in chemistry, it's really, well, science in general, it's really important. Significant figures tell me how precise a number is. Let's look at the very first question here. What I'm going to do is, let's see, let me allow myself to draw here. Okay. So the second number right here. So 3809,000. So we haven't really gone over significant digits. What it basically means is tells me how precise a number is. When I say precision, what does precision mean to you?
Precision means
Accuracy?
a bunch of numbers that are close together.
Mm-hmm. 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 Yeah, if I was shooting arrows, if I was shooting darts at a dartboard and all my darts were going in the very same place, that's very precise, right? And which is different, and this is something we'll talk about later, which is different from accuracy. That's different. Accuracy means you get the right answer. Precision means you get the same answer. So if something's precise, it means I can get the same answer over and over and over and over. Precision also means, how close to a particular number can I be? And this number right here tells me that if I put it's 3,809,000. So does this number tell me that it's not 3,809,001? Would that be accurate to say?
Yes.
Okay. Anybody disagree?
Maybe.
Maybe. I like that answer. Maybe's a good answer.
Because that could be 3,809,000X.
It could be, yeah. Actually, it could be a lot of different numbers. Basically, what you want to do when you see a number like that, has it been rounded from something else? Okay. So for instance, this could easily, if I was to round that to the nearest 1,000, I'd get this answer, right?
Yeah.
If I was to round it to the nearest 10,
Also
I'd still get this answer. If I rounded it to the nearest 100,
same
I'd
thing.
still get that answer. And if I rounded it to the nearest 1,000, I'd still get that answer. So what that tells me is that these three numbers are not significant, because all this number is saying to me is that it's not 3,810,000 and it's not 3,808,000. It's basically rounded to the nearest 1,000. So the only significant digits are these four. And what these three numbers are here, what those numbers are is a placeholder, which tells me how big that number is. So it tells me it's 3,809,000. It's not 380,900, and it's not 3,809, but it puts it in the right register, basically. It says how big the number is. But as far as significance, that's the only significance to those numbers. So do you remember how to put things in scientific notation? Anyone tell me how you do
3
that? What does that even mean?
3.809 times 10 to the 1, 2, 3, 4, 5, 6 power.
7, actually. Oh, no, 6, you're right. Yes. It basically means take a number between 1 and 10, and then how many times 10 am I going to have to multiply it by? So that same number, 3809. If you want to do scientific notation, first thing you do is find out how many significant digits you have. And how many significant digits do we have here?
4.
4. And so 3.809, because it's always going to be a number between 1 and 10. So it's going to be more than 1, less than 10. So 3.809 times 10, and then our exponent, like basically how many times do we have to multiply this by, is 1, 2, 3, 4, 5, 6. We had to move 6 places from the 3. So that's our answer right there. So we have 4 significant digits. So the number of 6 significant digits will always be represented here, okay? Always be represented there. So one thing we've learned is that trailing zeros, if the decimal is on the right side, these trailing zeros are not important because they're not, well, they're not important, they're important, but they're not significant to the number. They just say how big the number is. They give no additional information. So we don't consider them significant. Now that's different from the first number here. So how many significant digits are there in this number?
6.
Very good. How'd you come up with that?
580900.
So how come these zeros are significant and they weren't significant before?
Because they are after the decimal point and after the first non-zero number.
Mm-hmm. That's right. But what I want you to take away from that is there's a reason those zeros are there. So if I write 100, that means it's to the nearest 100. It means the closest number I can come up with, it's not 200 and it's not 0, it's 100. So this is the number to the closest 100. So this is the only significant digit right there. On the other hand, if I write 0.100, why are these numbers now significant?
Because they're after the decimal point.
Yeah, but that's true. But why? Why are they there? Really is the question I'm asking. Why would I bother to put those numbers there? Why don't I just, isn't that the same thing? Aren't these two numbers the same?
More precise if you add the more zeros.
That's right. That's exactly right. The reason we put those 2 zeros there is because I measured them. It means this is a measurement. This is a measurement. The 0.100 means that I measured that number and it's not 0.99 and it's not 0.101. It's exactly 0.1.00. So those numbers are significant. They're only there for a reason. I only put numbers behind the 0 for a reason after a real number. Notice that these numbers, these zeros at the beginning are not significant because just like these trailing zeros, they only tell me how big or how small the number is. So if the zeros are before the decimal, it tells me how big it is. If the zeros are behind the decimal, it tells me how small the number is, but it doesn't give me any more precision. These two numbers tell me how precise that measurement is. Yeah, is there a question?
So if the number is, let me write this, 100 dot.
Yes, 100 with a dot behind it.
Does that mean it's 3 6 fixed?
That's right. Because if I So this is something you're not going to see very often, but you will see in the chemistry class. If I write 100 with a period, with a decimal point, that means it's not 99 and it's not 101. It means it's exactly 100. And so that's 3 significant figures. Okay? So if it's a measurement, 100 with a decimal place is 3 significant figures. Now, where that doesn't hold up is if we're counting. Now, so if I said 1 dozen eggs is equal to 12, how many significant digits are there in the 12?
Infinite.
That's right. Because it's not a measurement. It's an exact number. It's precisely 12. And so it's 12 with an infinite number of significant digits, because we're counting now. We're not estimating. We're not measuring that it's approximately 12 or it's 12 plus or minus 1. No, it's exactly 12. The same is true, strangely enough, for something that will come up in measurements later on. 1 inch is equal to 2.54 centimeters. Exactly. And so these two are exactly the same thing. So we don't say there's 3 significant digits there. Basically, there's an infinite number, because those two are precise. It's exactly that. Okay, it doesn't come up very often, but it does come up occasionally. So to go back and answer that first question, what's our answer to the first number then?
6.
Right, there's 6 significant digits, but we need to, how do we write it in scientific notation?
5.80900 times 10 to the negative 1, 2, 3, 4, 5.
Right, so we go 1, 2, 3, 4, 5. Yeah, we move 5, so negative 5. So that'd be the answer. So we have to include those 2 zeros because they're significant. Because someone went through the trouble of designing a way to measure that so precisely that these 2 numbers are now significant. Because believe me, I used to work in mass spectrometry. Had some very expensive instruments, and they got more expensive the more accurately you wanted to measure something. So if I measured the mass of something that was like 1283, I'd have to spend another $1 million to be 12.83000. So it's really important to be able to measure that precision, and to show that you can measure something that precisely. So what about the third one? Who wants to help me out with the third one? How many significant digits do we have there?
3.
3, right? I mean, remember, any 0 is not significant after the decimal place until a non-zero number shows up, because it's just a placeholder. It tells us how small the number is. So right, so we have 3 significant digits. So what's wrong with that number? How come I can't write? I mean, it just says scientific notation. That's scientific notation, isn't it?
Scientific notation should be the multiplier should be greater than 1.
Right. Right. So I have to have, my number has to be greater than 1. So I just write down my 3 significant digits. So 1.24. So what do I change the -9 to?
3 and 7.
Negative 11.
Okay. Why 11? Or why
Because
7? Let's fight it out.
Oh yeah, 11. Because when you multiply the coefficient for 100 and you divide the 10 to the negative 9 for 100, so that's negative 11.
Right. Basically, what we did to make these 2 numbers equal, because they have to equal the same thing, right? So in order to do that, what we did here is we multiplied this by 100. So we got to divide this by 100. So if we make one side 100 times bigger, we got to make the other side 100 times smaller. So when we multiply them, we get the same thing. Right. So because we moved this one, 2 places, we have to take 2 places away from this. So that's why it's minus 11. Is everyone clear on that one? Why it's not minus 7? Because those two numbers got to equal. So if we multiply one side by 100, we got to divide the other side by 100. So it's the same thing. Okay. And what about the last one?
2.0200 times 10 to the second.
Okay. So how many significant digits did you came up with? 5 that time? But these are trailing zeros. That doesn't. So they're not significant, right? Because there's not a. Remember, these numbers past the 0 are not significant until we have a number, aren't they?
They're after the decimal point.
Right, but there's no number after the decimal to tell us that it's just, isn't that a placeholder?
No, number before the decimal.
Right, there's a number before the decimal. Doesn't matter. It doesn't have to be 2.0220 because that's an actual number. This means that 2.200, those 2 zeros are there for a reason. It means a measurement was done where it's not 2.201 and it's not 20199. So those 2 zeros there mean that measurement was done with that amount of precision. And so we have to show that when we give it in scientific notation. So we write all the numbers down. So 2.2000 times 10 to the how many?
Second.
2, right, because we move it 1, 2 to make 200. So 2. Excellent. So it's this goes back a little while, right? You probably haven't had to do scientific notation in a while, unless you're taking another science class at the same time. But yeah, this comes up a lot because we express a lot of things in scientific notation, particularly really big and really small numbers. We generally don't use them in sort of just everyday use. Like a lot of the time, a lot of our examples that we do, we won't need scientific notation because the numbers will be relatively small or relatively large. But when they're huge or tiny, we need this, or else we're going to be writing ridiculous things like this. And when I look at that, I don't know how big or I don't know how small that is. I need to count all the zeros. It makes my head bleed. But if you give it in scientific notation, you immediately can see how big it is, or immediately see how small it is, and you don't need to count them. So this is when we use scientific notation for like this, either big ass numbers or really, really small numbers.
When do you use scientific notation instead of a prefix?
Instead of prefix? What do you mean by prefix?
Like a microliter. When would you use microliter versus 10 to the negative 6?
Oh, actually, that's something we're going to be doing in a minute. When you're doing conversions from one unit to another, that's essential to do that, because you can't take something like microliters, which is 10 to the minus 6 liters, and then convert that you can't take microliters and then convert it to liters. You can't use the number in microliters. You have to convert that to liters in order for your conversion to work. So that's when we don't use it. If I'm just giving a measurement, and the measurement is like 0.00012 liters, that might be easier to go 1, 2, 3, 4, 5, 6. Oh yeah, it's 120 microliters. Because it's just easier to write. But if you're going to have to do the conversion, if you're doing like a lot of conversions, and we're going to do a couple of those problems, if you don't convert kilometers to meters, or if you don't convert, microliters to liters or whatever, you're going to get the wrong answer at the end when you're doing a lot of unit conversions at once.
Okay,
But
so
that's when you'd need to.
you just
So
use scientific notation for converting.
Yes. Yeah.
Okay.
Really important for doing conversions.
And then just the prefixes for general writing.
Yep.
Okay.
Yeah. Yeah. I mean, you won't get points off. I mean, if the answer to a problem is this, you're not going to be marked wrong if you don't give it in terms of this, because they're both the same. Unless I say expressly in the problem, I want the answer in microliters. So if you don't give it in, but if I say, what's the volume, you can give it whatever units you want, because I didn't make it clear which units I wanted. But if I make it clear which units I wanted, then you have to give it to me with the proper notation.
Okay.
Yeah, I mean, you could give it in gills if you wanted to. I don't know why you would, but whatever volume you want it, gallons, whatever. If it's not made clear, but we'll be using the metric system for this, because that's what scientists use.
excuse me.
Yeah, go ahead.
So for light speed equals to 2.9978 79 etc. times 10 to the 8th power meters per second.
Mhm.
How many significant does that have?
Just count
infinite?
just count the number of, that's a measurement. That's a measurement. So however many digits are given there, that's how many significant figures there are.
Oh, okay.
Yeah. So however many there were, I can't remember how many you said, either 6 or 7. But yeah, all those numbers before the times 10 to the, that's the number of significant
So
figures.
like light speed is a gravitational acceleration. That's all. How many significance the significant figures the problem gives, right?
Exactly. So yeah, in all of our problems that we're going to do, or test problems that you're going to do yourself, you can only answer the precision of your answer can only be as precise as the numbers you're given. And so actually that's a really good, why don't we just go to the second one and see how that works. Yeah, so these are numbers. So these are numbers that you're given, and we're going to learn there's a difference between insignificant digits when you're multiplying and dividing than when you're adding and subtracting. It's not the same thing. So why don't we do the first one, and I'll show you what I mean. So when you're multiplying two numbers together, the answer you get can only be as accurate as the least accurate number. Okay, so like for instance, if I was to say to you, 1 gallon, let's say 1 gallon of milk was like 4.53867249 kilograms or whatever. Give me about 2 of them. What's the weight of about 2 of them? Now, there'd be no point in like taking all these numbers when I just asked you for about 2 or 3. All of these numbers then become meaningless, because the other thing I've asked you to do to it, I've given you a number with no precision to it. So if I was to take 2 times that number, what would the answer be?
Does that 2 means you mean two of them, right?
Yep. How many kilograms would that be?
Would that also have? I mean, that too can be infinite significant figures, right?
No. There's only one significant digit here.
I mean, you said two,
that
but
two just means it's not 1 and it's not 3. That's all that means. So how many significant digits can there be in my answer?
1.
1. That's right. Because basically what I'm saying is I've measured something extremely accurately, but then I want around 2 of them. So basically I'm throwing all this accuracy away because I'm not giving you any accuracy here. So basically you're limited by the least accurate number. So what's my answer here?
9.
9.
9.
Yeah, so what you would do is you'd plug all the significant digits into your calculator, and then whatever the first number came out, but if it was like 9.5, the answer would be 10. But I'm thinking it's going to be closer to 9. So yeah, so the answer is 9. Even though
Excuse me?
So well, let's plug it in.
That's 9.076, etc.
times 2. Yeah, so the answer is 9.077. Yeah, and so since this is 9.0, my answer is 9.
Excuse me.
Yeah, go ahead. You had a question?
So you said a dozen has many significant figures.
Right, because a dozen isn't a measurement. A dozen is a count. And there's a difference between a measurement and a count. If I can count something, that means I know precisely how many. Like there's number of people in the class. If I can count each and every one exactly. If I'm measuring how many people are in the class, there's an estimation there. There's some uncertainty there. And that's what we mean by significant digits. So if I was, because with significant digits, like when you're measuring something, and we'll get into this a little bit later when we're actually doing some measurements. When you're using significant digits, you give all the numbers you can actually read, and then you estimate the last one. So if I was to look at, let's say I had a graduated cylinder or something, I can read 9, 10, and then there's little marks to show each decimal in between. So I could say, okay, it's 9.9, and then I would estimate that last number. And so let's say it was 9, like I saw it was a little bit below halfway between 9.9 and 10. So I estimate this number. That number is also significant because I know it's not 9.90 and I know it's not 10, but I don't know what it is exactly, but it's close to 4. So this number is also significant. So that would have 3 significant figures. And so when we're in the lab, your precision is extremely important to be able to recognize how precise can I measure something, because that's what scientists need to answer every day when they put something on a scale, when they measure the volume of something. How precise is that? You need to know that because it makes a huge difference. Like if you're dosing a patient with a drug, you got to be precise. You can't be off by, it's around 2 milligrams per kilogram. Well, no, not if 2.1 milligrams will kill them. You've got to be really precise. You have to know how precise your numbers are. Okay? So let's do the first one here. Since we're multiplying these two numbers, what's our answer going to be?
240.
Yeah, so 240. So we do that part. 240. But how many significant digits can we have in our answer? 4. We can only have 4. So here we've got 6. With the 40 we've got 6, but with the 6 we've only got 4. So what's my final answer going to be?
240.0.
That's right. So 4 sig figs. And believe me, you're going to get tired, and I'm going to get tired of writing it. I'm going to be putting this on your on your tests a lot. And the reason I'm such a stickler for it is because it's really, really important. Like when you're doing actual science, these numbers matter a lot. And so getting them wrong can, especially like I said, if you're going into nursing or you're going into medicine or you're going into pharmacology or something like that, where you're like, you're giving drugs to real people, this number is super important. It could make a huge difference. So that's why I'm such a stickler about it. So what about the next one? When we're adding, what are we going to do? What would you suggest when we're adding numbers together? How do you think that
Don't
works?
you also need to express the 240 in scientific notation for the first one?
Oh, you're right. You're absolutely right. I asked for scientific notation. Right. So what would the answer to that be?
2.400 times 10 to the second.
Right. Yeah, that's the same. So we've divided this number by 100. So we need to multiply the other side by 100. 10 to the second. That's right. Now, when we're adding numbers, it's different.
Decimal places.
Actually, the way I like to do it is to just put them on top of each other. So 6.79. So that's how you would add them, right? So then you just add them together like you would. So giving all the digits, what would be our answer to that?
37.237.
237. Okay. So is this the correct answer?
No,
How come?
because the first one has 3 decimal points and the second one has 2 decimal points.
Right. The second one only has 2. So basically, we don't know what that number is. That number could be any number from 0 to 1, 2, 3, or 4. We don't know what it is, because remember, everything in these numbers you have to consider is a measurement. So that could be 6.790 or 791, 792, 793, 794. We don't know what it is. And so this number can't be significant. It can't, because we don't really know what it is. But so is this the correct answer?
No,
How come?
because 7 is greater than 5.
Right. So we got to round it. So that would be the correct answer. So when you're adding numbers, it's the number of past the decimal place that matters. So if I have like a really, really big number with a lot of trailing zeros and I'm adding a very small but precise number to it, it doesn't really matter, because my big number, let's say I have 100 and I add to that 2.1936. Well, that's all kind of wasted, because with my 100, I don't know what comes after it. So basically my answer is 102, because I don't know what any of these other numbers will be. So it's not quite the same thing. You'll find that you just can't add or go to the smallest number of significant digits. It has to be, like, for instance, if this was 100 without the decimal place plus that number, the answer is still 102. So I took something with only one significant digit and I added something with like 5 significant digits, and I got something with 3 at the end. So so when you're adding or subtracting, it's different than the rule we use for multiplying or dividing, where you just take the number with the smallest number of significant digits and that's the one you use. With adding and subtracting, you actually have to do the addition and subtraction like this. Set it up like that so you can actually see who has the smallest number of smallest number of digits past the decimal place. Okay. Oh, so what's our final answer then for this question? So that's the number, but what is it in scientific notation?
3.724 times 10 to the first.
Yes, just times 10. 724 times 10. And you can put the 1 there. It doesn't really matter. It's assumed it's there. Okay. Now, what about the third one? Now, the third one, we're doing both addition and division. So going way back in time, do you remember what order we do these in?
We first do addition.
Right. We always do addition first and then multiplication and division second. So we do whatever in brackets first, if there's brackets, or exponents. And then after that, we do addition or subtraction. And then after that, we do multiplication or division. So we might as well put like a brackets there because it's basically the same thing. So we do the addition part first. So we've got 61.2, 88.5. So what's our answer there?
61.2 plus 88.5 is 149.7.
So how many of those numbers are significant?
4.
Yeah, all of them. So we took something with 3 sig figs and added it to another thing with 3 sig figs and ended up with 4. So now we've got 4. What about on the top? Our number on the top, how many significant digits does that have?
5 sig figs.
That's got 5 because if it's included in scientific notation, it's automatically significant. So basically we're taking 1.7800 times 10 to the 17 and we're dividing it by 149.7. So what would our answer be?
149.7. Do we need the times 10 to the 17th power after?
One thing we can do. What do you mean? Do we need it? Yeah, we definitely need it.
Well, that is 0.01189.
Sorry, what's
So the 0.
Yeah, you're fading out on us. Sorry. What I'd suggest, since if you don't have I don't even use a scientific calculator. I'm too dumb to use a scientific calculator. What I would do is put this in scientific notation as well, and so that would be, so that's our 149.7. So what's my 149.7 in scientific notation?
1.497 times 10 to the second.
1, 2, right. Because that way I can then divide this part and then divide this part separately, right?
Yeah.
So then I'm going to divide 1.78 divided by 1.497. So what's that number?
1.18904, etc.
1.18904. Okay. And then what's this part?
10 to the 15th.
10 to the 15. Yeah, we just subtract the exponent. That part's easy. Now we've got an answer. But the question is, how many significant digits do we use for this particular answer?
4.
4, right, because we have 5 up top and we have 4 on the bottom. And we can our precision is limited by our least precise number. And here, the number with the least precision is our denominator. So we lose these 2 and we just keep these 4. So our answer would be 1.189 times 10 to the 15.
So, me.
Huh?
Excuse me. So when we put this all in calculator, it would maybe a different number. It would be get maybe we will get a.
Hopefully you get the same number.
I mean, when we put all the things in calculator once, we will give different significant figures. Or
Yes, you will get, yeah, because the I don't know. Yeah, I mean, your calculator generally doesn't know about significant
yeah,
digits.
maybe we.
So, yeah, I mean, if you divide 1 by 3, for instance, it'll be 0.333333 indefinitely, right? But 1 divided by 3, there's only if both those are measurements, then you can only give it to 0.3 because there's only one significant digit. So yeah, so calculators don't know about significant digits, but you now do. So you would have to get whatever answer it is and then round it to 4.
I mean, in this kind of problem, like we get 61.24 plus 88, and I put all the things in one calculate, in one
Okay.
in one calculation.
So
And
what did you get?
so I mean, if that's the case, would I get a wrong answer?
Well, what answer did you get when you did that?
I mean,
I mean, hopefully you get the pretty similar answer.
I mean, I'm not talking about this problem.
Oh, okay.
So we did the adding and subtracting separately.
Mm-hmm.
If we put this in a calculator, we put
You'd have to put brackets around it.
Yeah.
Yeah.
So what I meant is for the result of adding and subtracting, we rounded it up, right?
No, we didn't do any rounding. Well,
I mean, if the decimal places are different, we should round it up, right?
Oh, I see what you mean. Yes. Yeah.
So,
in this instance, we didn't have to do any rounding.
so if
one thing I should point out, the number of significant digits. If, on the other hand, here, we did have to round, I wouldn't round until we got to the final answer. That's a really important thing to remember. It's something that students make a mistake with all the time. So, for instance, if we used this first number instead of this second one, I would take all the digits. If I was to then take this number and then multiply it or divide it by something else, take all the digits. Don't round it yet. So I would use all the digits in that answer. I would use 30. Let's see. So 30.447 plus 6.79.
that's
So
37.
I'd get 37.237. And I would use all those numbers because I'm not done yet. So basically what you want to do is not limit the precision in your final answer by limiting the precision in any one step. So what I see students doing all the time is they will round all their numbers and then keep rounding until they get to the end. And by the time they've got to the end, they've rounded so many numbers that there's no precision left in the final answer. So in this instance, your final answer will still have only 3 significant digits in it, but you should carry over all of the digits until you get to the final answer. Do you understand the difference?
Yeah.
Yeah, because there's going to be a lot of like, especially in lab where you're doing a lot of calculations of measurements. So if I take if I round my first measurement and then I round the second one and then I round their product and then I take that product and I multiply it by something else and I round that, by the time I've got to the end, I don't, the answer I'm going to get is really imprecise. So take all of the digits. If your calculator can handle, 15 digits, just use them all. I had some students the last term who, when they were showing me their answers, they'd have all the digits there, which is fine. But you need to know how many should be in your final answer. That's the key.
Okay.
So if you just have, if the question is just one step, like adding these two numbers together, then you only give me the proper number of significant digits for that final answer. But if that's just the first step in a long series of steps to get to the final answer, carry over all the digits. It'll make your final answer more precise. I hope that makes sense. Because we'll go over this again because that's going to show up a lot in problems where if you round too early, you lose out on the precision of your final answer. So let's do the last one. Who's got a suggestion on how to approach that?
Before we do that, may
Sure.
I ask?
You
So,
can ask anything you like.
do we use this? I don't know how to say it in English. Do we use this
approximate?
sign or equal sign?
Approximate?
Uh-huh.
Yeah, we use that all the time.
I mean, when calculation, we use approximate sign.
Yeah.
Okay.
Yeah, we use that sometimes, sure. Yeah, I mean, if you, for instance, if you calculated something was to be like, 11.623, 11.623 or 11.6, let's just say it's 11.6. You could say that that's approximately 12. But I mean, if you went through the, like if this was the answer, like how many somethings, like actually at the end, the last question, like basically asks you how many things could you make with a certain amount of material. So if my answer was 11.6, I would, you could say 11.6 or approximately 12. And then that's when you would use the approximately.
Like for the second question, 30.447 plus 6.79, I got 37.237. Do I say approximately 37.24?
No, you'd say it equals, because only if you were asked like what's basically you only use this for whole numbers. So if you need to round it to a whole number, you would use the approximately.
Okay.
Yeah. You use the equals like when you're measuring something and that's as precise as your answer is going to get. That's equals.
Oh, okay.
Yeah. Yeah. Good question.
Well, it sounds a little bit weird, but yeah.
A lot of things are a little bit weird, but yeah, we don't use approximately much, and basically only if you're rounding to a whole number is really the only time I can think of when you would use it.
Okay.
So for the last one, how would we do that? Since we got these two huge numbers, how do we
change one of to 10 to the 15 or 10 to the 16? Change one of them to
right. We get them to the same register, so then we could automatically deal with them. So what should we do? Should we make one bigger or make one smaller?
Make ones bigger.
So take the 8 and make that to the 16. So we take 8 times 10 to the 15. So that's going to be 0.8 times 10 to the 16, right? So we're going to divide that by 10, so we need to multiply this part by 10. But remember, we need to carry over our significant digits. So that would be
0.8000.
000 times 10 to the 16. And then with that, we add 7.20 times 10 to the 16. So what's our final answer going to be?
8.00 times 10 to the 16.
Right, because we're limited. Again, now we're not multiplying anymore. Now we're just adding. And so we've only got 3 significant digits. We only got 2 past the decimal place. And so that's what we're limited by. You can only have 2 past the decimal place. So it would be 8.00, 2 past the decimal place, times 10 to the 16.
The decimal point doesn't mean decimal point here. Because
no, it means the same thing. We're still dealing with a decimal place.
But it's scientific notation. It means it means a huge number. It doesn't mean decimal point.
Right, but it also means we don't know what these numbers are. So with 8.000, we can measure these 2 zeros. Means we measured that exactly. Well, not exactly. We measured that with much more precision than we measured the bottom. And so these 2 numbers, XX for 7.20, we don't know what they are. And so we have to limit our precision right there. Past the decimal place. So if this was 3.80, our answer would be 11.00. So we'd have 4 significant digits, but we'd still only have 2 beyond the decimal place.
Okay.
Yeah, so we'd be taking a number with 5 significant digits and adding a number with 3 significant digits and getting an answer with 4. So that's why, you always look past the decimal place and see how far can you go until basically just breaks down and you don't get any more. You don't get any more answer. You don't get any more precision. And with this instance, it's 2 places past the decimal place.
So if 2044 plus 500, you get 2500.
Sorry, what 2 numbers are we adding?
And 2044 plus 500.
2044 plus 500.
You get 2500.
Yes.
Okay.
Yep, exactly. Because basically what we'll get to, you just add them together and see how many points past the decimal, or none. No, wait a minute. No, we would get 20. No, we would get 2544. We would get 2544
So
when we add them.
But if it was 2.044 times 2 times 10 to the third plus 5 times 10 to the second, it would treat it differently.
Yeah, that's a good point. Let me think about that one.
You just get 3 or 3,000 without the decimal places. You only have 1 sig fig, which is
That's a good question. I have to think about that one. Yeah, I guess you would only if you convert it to scientific notation. That's a good. I hadn't thought of that. Yeah, let me think about that. Yeah, because if you don't convert it to significant digits, I think we get 2544. But if you do put it to significant digits, you get 3,000. That's a good point. Let me think about that one. I always like it when there's like questions I don't know the answer to.
I have another one. Like with this 8.00 times 10 to the 16.
How
do you write that out to show that you have those 2 significant figures when you write it out? Like when you
Oh.
add the 16 zeros, how do you show that it's only 3 sig figs?
Oh, 8.00 times 10 to the 16.
Yeah, but like when you write it out with all the zeros or whatever,
Oh, yeah.
how do you show that you have those 3 only?
By showing it in scientific notation.
Okay.
Yeah.
That's
Yeah, because if you just have 8 followed by 16 zeros, you have no idea how accurate that number is. That's why scientific notation comes in so handy, because without it, we only think there's one significant digit. We wouldn't know. Yeah, so you'd have to show it in scientific notation. So yeah, this is new for a lot of folks. We haven't even talked about the mole yet. But everyone remembers? Anyone know what a mole is?
Calcium is 40. P is
So you're giving me a number without a unit. That is
calcium is 40 U 40
U. What the hell
Is
is a
it
U?
grams per mole?
Yeah.
Right. So a mole is basically how we calculate an amount of a substance that is involved in a reaction, because a mole is the sort of our basic unit of reactivity, and so and it relates to how big an atom is. And so, for instance, if you need to know these things, what I would suggest is going to, I think I put it, I don't know if I put it in the
Going to learn
canvas or
more
not.
basic chemistry.
This is a great place to go. ptable.com. Just basically periodic table, ptable.com. So I'll take you there to show you what I'm talking about, because it has all kinds of really cool information. How do I get to it?
Table.
Oh, here we go. Okay. Hopefully you can see my computer screen. You're seeing the computer screen now, or?
Yes,
Okay.
I see it.
All right. So ptable.com. So if you go here, basically shows you the periodic table and gives you all kinds of information you can use. And so these are all, and we'll go over this little, in preceding lectures. These are all weights. These are all atomic masses. And so it tells you how big or how small each atom is. Now, these masses are given in what's called atomic mass units, which, what the hell is that? Well, it means a proton weighs 1, a neutron weighs 1, an electron weighs 0, basically. And so
It's an average, right?
Huh?
It's an average of the all the what's this thing?
Isotopes. Yes.
Isotope.
Yeah, these are average numbers. So what that means is that there's a lot of different flavors of these atoms with different numbers of neutrons in them. This is the average mass. If I took like 1 billion atoms and measured the mass of all of them, this would be the average of all of them. It also equals the number of grams there are in 1 mole of that particular element. And its moles are what we care about, because atomic mass units it's not a real number. It doesn't really mean anything. What can I do with that? I can't do anything with that information. But grams in a mole, that I can do something with, because we can actually measure grams. So we can measure grams very easily. We just put it on a balance and measure grams. Now, moles, like I mentioned, is how we measure how much reactivity or how much reaction a particular amount of a substance can undergo. And so it's our basic unit of reactions for a particular element. So this is their mass. So we're looking for calcium. There's calcium, calcium, calcium. Here we go. So 1 mole of calcium weighs 40.078. 40.078 grams. That's important to remember because 40.078 doesn't mean anything. 40.078 grams does mean something. So what are the other elements we were looking for? There's calcium, and I think what, phosphorus was another?
30.974.
So there's phosphorus.
Oxygen.
30.974 grams in a mole. And then oxygen, we go over here, 15.999.
15.999 grams
Right.
per mole.
Right. So that basically tells us that pretty much all the oxygen in the world has 8 protons and 8 neutrons, because it's this first number on the top, on the left, that's the atomic number. And we'll learn about that as we go. The atomic number tells you what? Anyone tell me what the atomic number means?
Many protons that the atom have.
Right. It's the number of protons. And it's the number of protons defines what the element is, not the number of electrons and not the number of neutrons, because the number of neutrons can vary. So because its average mass is 15.999, that tells us that almost all the oxygen in the world is exactly 8 protons and 8 neutrons, and a very small number of it only has 7 neutrons, but very, very, very little of it. So is that all of the elements in that particular molecule? Calcium, phosphorus, and oxygen, is that it?
Is that a molecule?
What's the formula we're looking for?
Calcium
It is
phosphate.
calcium phosphate, right? We haven't got to that yet, but yeah, it's calcium phosphate. But there's only 3 elements in it: calcium, phosphorus, and oxygen. So let's go back to
To the page.
Yeah, here we go. Yeah, so we're going to. Come on. There we go. So hopefully, are you seeing the full screen now?
Mm-hmm.
Okay. All right, here we go. So we've only got 3 elements. We got calcium, we got phosphorus, and we got oxygen. The question is, so this is, now calcium, whoops, let me go back. Calcium, damn it. Stop doing that. Here we go. So why is it doing this? I want to draw something. Let me draw something.
Where's your mouse?
It's not the whole screen, Professor. Just
You're not
small
seeing?
in the middle.
You have to pause it. The time it's going. Not you, P.
Okay. Now let's
I think now it's gonna work.
see if, there we go. So yeah, so we have 3 elements. So our elements are calcium, phosphorus, and oxygen. But this is what? Not an element. What do we call that?
It's not a molecule.
Compound.
It is. Yeah, it's either you can call it either a molecule or a compound.
Yeah.
Basically, it's a collection of atoms that are chemically bound to each other, and we'll learn how they bind to each other a little bit later. Basically, it means they're sharing electrons in some way. So all these elements are sharing electrons with each other. And so they're all together as one unit. So this is now a compound. And so we have to figure out, when we have this compound, how much of it does a mole weigh? Now, we need to figure that out, we need to know how many atoms there are, how many atoms of each element there are. Now we know with calcium, one atom is 40.078 grams in a mole. And with phosphorus, it's 30 point, was it 971?
97.
Grams in a mole. And with oxygen, it was 15.999 grams in a mole. That's for one atom, okay? But the question is, how many atoms of each one of these do we actually have? So how many atoms of calcium do we have?
3.
3, because, yeah, you can see it right there. The number is 3. That's fairly obvious. What about phosphorus? How many?
PO4 is at
2.
2, that's right. If the number is in brackets and outside of it, we multiply everything inside by 2. And so this is what's called a phosphate ion, PO4 minus 3. We'll learn about how to do charges a little later as well. That's called a phosphate ion. It's an ion that has more than one atom in it. And so, and there's 2 of them associated with calcium. So because there's 2 of them, that means there's 2 of these, there's 2 phosphates. And how many oxygens are there?
8.
8, right, because there's 2 whole things of those. So there's 2 phosphoruses, and there's 8 oxygens. So what do we do next?
Add them together.
But when we're multiplying, since this has 5 significant digits and this is only 1, should our answer have only 1 significant digit in it?
No.
No. Why not?
Counting.
Exactly. I'm not measuring 3 calcium atoms. I'm counting 3 calcium atoms. Very good. So my answer should have the same number of significant digits as this does. Actually, it could have more, since this is an infinite number. So basically, I would just count the number of digits past the decimal and I'd keep them all. So what's my first answer?
120.234.
And again, keep them all. Keep all of them until you get to the end, and then figure out how many significant digits should I have, okay? And the second one?
61.942.
942, okay. And the third one?
Third one, wait a minute.
Man, they're making you do all the calculations, dude. That's not fair.
127.992.
There you go. 992.
Phosphorus be 30.974.
So what's our final answer?
310.168.
168. Yeah, because all of these numbers are significant. And so we're going 3 past the decimal place. And so we keep them all. Now, this would be if you looked on whatever you used as your source for atomic masses. They're not always going to have the same number of digits. Like, for instance, oxygen often is rounded to 16.0. If that's the case, if that's the number you're using, then you can only use 1 digit past the decimal, okay? But I would recommend you bookmark ptable.com right now, because you're going to be using it over and over and over. And it has all kinds of really important information like densities. And when we do electron configurations, like how are its electrons configured around the nucleus, you know, what color is it when it's a metal? I mean, all that kind of stuff. What ions does it form? It has pretty much everything you need in there. So I keep that as a bookmark because I'm going to use it all the time. And you can double check your answer on that one. You can actually just go to Google and say, molar mass Ca3PO42, and it should give you the answer. So you can always double check. But if you did that, like I said at the beginning, if you just did that, if you gave me an answer of 310, whatever, you don't get any points for that because you didn't, you gave me an answer, but you didn't show me how you got there. So yeah, you get half, but you're not going to get all the points on a test. Just getting the right answer isn't that important. How you get to the correct answer is a lot more important. Now, dimensional analysis. Now, what this means is basically you're just converting one unit of measurement to another unit of measurement. And we're going to be doing this all the time. You're going to get sick and tired of this. But it's something we need to do all the time because we're always getting grams per liter, grams per mole, moles per liter. And so you're going to get all these different units, and then you're going to be asked about a certain number at the end. So you're going to have to make sure that you convert all those units exactly right, or you're not going to get the right answer. So for instance, this first one gives us milligrams, and we want to convert those to kilograms. So the way to sort of do this is basically convert them both to grams, and that way we can work it out. So anyone know how many milligrams there are in a gram?
Negative third. 10 to the negative third.
So there's 10 to the minus 3 milligrams in a gram?
Sorry, 10 to the third milligrams.
Right.
To a gram.
Right. Milligrams are smaller. So 1 gram is equal to 1,000 milligrams. Or the other way of looking at it, 1 milligram is equal to 10 to the minus 3 grams. Either way is correct. So what about kilograms, though? What's the difference between 1 gram and 1 kilogram? How many grams are there in a kilogram? Which one's bigger first?
Kilogram is bigger.
Kilogram's bigger. So how many grams are in a kilogram?
1,000.
1,000. Yeah, kilo means 1,000, and milli means 1,000th. So milli means smaller, kilo means bigger. So the way to do all of this, the way I like to, there's a couple different approaches to use. The one I like to use is because it's simpler, and I need things to be simple in my life, is you can do these either one at a time, or you can do all the calculations at once. So in other words, so I have 8.23 times 10 to the 11 milligrams. Now, I can either go directly from milligrams to kilograms, or I can go through grams. I kind of like going through grams. So what I'm going to do is put grams on the top and milligrams on the bottom. That way, if I have the same unit on the top and the bottom, I can cancel them out, okay? And the unit I want to be left with is kilograms. So I'm going to put kilograms on the top and grams on the bottom, because I want to cancel out grams and I want to be left with kilograms. So basically, when I'm doing these conversions, I always put what I want to end with on the top and what I want to get rid of on the bottom. Because what I want to cancel, I'll have on the top and the bottom. That'll cancel out. What I'm left, and I'll be left with the number I want. Okay. So there's 2 conversions I'm going to make. So the first one is grams per milligram. So there's 2 ways I can do this. I can either put 1 gram on top and 1,000 milligrams on the bottom, or I can put 1 milligram on top and 10 to the minus 3 grams on the top. Either way, I kind of like using whole numbers. So what I'm going to do is put 1,000 milligrams on the bottom and 1 gram on the top. So what do I do on the second one here? How am I going to kilograms and grams? What do I put on the top? What do I put on the bottom?
1 over 1,000.
1 over 1,000. Right. And so this is why I always say, always have the units there, because it's real easy to make a mistake. If I just had, times 1 over 1,000 times 1 over 1,000 without any units there, I could easily flip one or the other and then screw up my whole problem. If I have the units there, I know exactly what I'm doing, because here, this tells me that grams are going to cancel out, milligrams are going to cancel out, and the only unit that's left is kilograms. So I must have done it right. As long as I didn't screw up putting these in, my 1 in 1,000 or 1 in, 10 to the minus 3, depending if I didn't screw that up and I'm left with kilograms, I know I've done the problem correctly. Okay.
Right.
So what I've got is 8 times 2, 3 times 10 to the 11 over there times what? What have I?
10 to the negative 6.
Right. So I've got 10 to the minus 3 here. And I multiply it by 10 to the minus 3 here. That's 10 to the minus 6. And that's my girl. Shh, 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 shh. And that's my boy. So what's my final answer?
10 to the power of 5.
Sorry, what is it?
8.23 to the 5.
10 times 10 to the 5th. Not the correct answer, though. How come I'm not giving you full points for that answer?
Kilograms.
Yes. Yeah, you're giving me the number, and that's all well and good, but you didn't give me the unit. So I'm going to jump down your throat and yell and get very angry. Yeah, so it'll be 8.23 times 10 to the 5th kilograms. And I can't emphasize that enough. Gotta have a unit. Pretty much every answer in chemistry has a unit after it. And so, well, except for this second one.
Excuse me.
So yeah, always have a unit. Yes.
My calculator can do units conversion for me. So can I rely on that?
Dang. I guess it depends. Yeah, but yeah, that's sure. But you still have to show it.
Okay.
You still have to show how you did the conversion. So
my calculator,
if your calculator can do that, then good for you. But I still need to see the conversions that you did. Yeah. So again, if I asked you, if this question was on a test, and you gave me the answer 8.23 times 10 to the 5th kilograms, I would, oh, that's all well and good. You're getting half the marks.
Okay.
Because you didn't show me how you did that. So yeah, I'm glad for you and your calculator. I wish I had one that did that.
For whatever my units are, as long as I put units, it give me SI units.
That's great. That's great. Yeah, but you need to show it on the paper to see how you got there. Okay.
Okay.
All right. So what about the second one here? Let me clear everything.
Oh, I have a quick question.
Oh, sure.
How are you taking attendance for these recitations?
I think I'm pretty sure that Zoom does it for us.
Oh, I see.
I'm hoping.
Okay. Yeah.
I'm pretty sure it does, but yeah, I need to. It's something we hadn't had to do earlier, so yeah. But I'm pretty sure it does, and if not, I can sort of add a poll in the middle. Actually, let's add a question.
How many moles of water?
Oops, type my question.
Bowl 500
There you go. And there you go. Oh, answer 1. Yes. Oh, I'll try this one. No. Okay. So, yeah, so there's a poll out there. So I guess if you answer that, you attend it. So
Oh, I can't see. I can't see.
can you see it? Is it there? I haven't used this before, so if it's not there, let me know.
Not.
No, sorry.
Not there?
Yeah, no. There.
I don't see it.
Oh, sorry. Here we go.
Are you here? Yes or no?
Now you can see it?
Yeah.
Okay.
Looks good.
Yes.
Of course,
What if some,
I don't know if there's names there. If there's no names, it'll just be like, yeah, there's people were there. So yeah, I'll find out.
That's tough.
I'll find out how to do
what
that.
if someone says, no, I'm not here?
Okay, thank you.
Well, then, yeah, if you just answered the question, then obviously you were here. All right, let's go back to the. Why won't it go back to the? Oh, damn it! I can't get back to the. Okay. There we go. Okay. So second one. So since we've gone over moles, what information are we going to need for the second question? How many moles of water? Hopefully you know that H2O is water at this point. How many moles of water are in 500 grams? What information do we need to answer that question?
Hydrogen's molecule, molar mass and oxygen's.
Right, we're going to need the molar mass of a mole of water to answer that question. So when I do these let's do that first. So we need the molar mass of H2O. So to do that, we need to count how many atoms are in the molecule and the mass of each one. So we have, how many atoms of hydrogen do we have?
2.
2. So we have 2 atoms of hydrogen, and we have how many of oxygen?
1.
Just 1. So we need to know the mass of 1 atom of hydrogen. Anyone tell me what that is?
1.008.
1.008. Remember, that's grams per mole. It's also atomic mass units, but we don't really care about atomic mass units because I can't walk over to a balance and weigh out atomic mass units. Grams I can measure. So it's grams per mole is really the important thing about that. So what about oxygen? We already did oxygen, right? It was 15.999 grams per mole. So there's 2 of those. So what's our final answer?
18.015.
18.015 grams per mole. And it's the per mole is so super important. I'll show you why in a second. So whenever you get a dimensional analysis question, first thing I do is I write down the number I'm given. Okay, so the number I'm given is 500 grams. So I write that down, 500. And there's a decimal, which we know now is important. So so that's the number I have. Now, what's the number I want? So I want to do something to that number. At the end, I'm going to get moles of water. So I'm going to have to multiply this by something to get me moles of water. So if we go back to the approach I used the last time, what unit am I going to put on top, and what unit am I going to put on the bottom here?
Moles.
Most program.
Right. So I want moles. I want to end up with moles. So because that's the unit I want, I'm going to put that on top. So I'm going to put moles on top. And the unit I want to cancel on the bottom. And we just calculated the molar mass of water, right? So we
S after a unit.
I'm going to either have, S or just one.
Mhm.
I mean, we want to end up, basically it's mole is the unit we're going for. So we have more than one, it's moles. But yeah, it's mole is the unit we're going for. So, and we already calculated that 1 mole is how many grams for water? We just did the calculation.
18.015.
Yes. 18.015 grams. And so I can get rid of my grams and I'm left with moles, which is what I want. This tells me that I have done my dimensional analysis correctly. Now, what people will do all the time, students do this all the time, well, I can just divide by 18.005 and give you the answer, right? No, because I don't want you to divide anything, ever. And the reason is I want you to multiply. Always, always, always multiply. And the reason for that is you don't know where the units go if you're just dividing, right? If I'm just dividing one number by another number and there's no units there, you've just got a number and you have to basically assume that you set it up properly. You don't know if you set it up properly, but I got a number and I ended up with a number, but you don't know whether you set it up properly. If you multiply instead of divide, you always know if you set it up properly and with the units there. So that's why I always include the units. Even now, I mean, I'm an old man, but I always include the units because I'm not exactly certain if I've set up my numbers properly. But if I have the units associated with them, I know that I have, okay?
What if the person is confident?
That's great, but if you don't show me your units, you're not getting full marks.
I mean, he shows your unit, but he used division.
As long as I see the units.
Okay.
Yeah, I mean, obviously, I'm not going to multiply this number by 1 and then divide by 18 to get my answer. Obviously, I'm going to divide 500 by 18.105 to get the answer, right? Mm-hmm. That's what I'm going to do. But this by doing it this way, by setting it up like this, I know that that's what I'm supposed to do.
Okay.
That's the key, because a lot of times what you're going to have is you're going to have all kinds of numbers on top and bottom, particularly where we're doing like moles and grams and liters and moles and density, and you're having all these things together, and they're not always going to be just one. You're going to have a number of different things. So if you don't set it up properly with everything in a row and crossing out all of the units, there's no way you're going to be able to get that right. So that's why I just sort of just set this up as, this is my system. I'm always going to use the same system every single time. And that way I'm always going to get if I get the right units, I'm going to get the right answer, like 99 times out of 100. Okay. So let's finish the problem. So how many moles is that?
27.75.
27.75. Keep going.
4648.
4648. Moles.
Okay.
So that is not the correct answer. Why?
Street sig fix.
Exactly. There's 3 significant digits here. There's 5 significant digits there, and we're doing multiplication division. So we're limited by the least precise number. And our least precise number in this particular series is this one. So we're limited to 3 sig figs. So what's our final answer going to be?
27.7.
Nope.
27.8. It's moles. of
0.8,
water.
right, because this is a 5, so we
Eight.
round up. So 27.8 moles. So there's two things you need to have the exact correct answer. You need to have units, and you have to have the right number of significant figures. And of course, you know, all the stuff that went into that to get full marks on a test, okay? But yeah, so I'm going to let you guys do these two. One bit of information you're going to need, you're going to need to convert miles to meters. So you can just look up like how many meters in a mile, or you could look up how many kilometers there are in a mile. And you can convert miles to kilometers and then convert kilometers to meters. There's 1,000 meters in a kilometer. So you can do it that way. But in this instance, you're going to be converting two things. You're going to be converting both miles to meters and converting hours to seconds. And so that's when setting up your dimensions so that everything cancels out is super important. That there's no way you can just, you know, divide or multiply something. You've got to set up everything correctly. And this last one, in order to figure that out, you need to know that 1 liter is equal to 1,000 cubic centimeters. That is key. And another thing to remember is, let me erase some of this. A very common mistake, because I make it a lot my own self, is, so 1 centimeter is equal to 0.01 meters, or 100 centimeters is equal to 1 meter, right? If you have a ruler, like 1 foot is about 33 centimeters or so. So there's 100 centimeters in a meter. So if I have 1 meter over 100 centimeters, this is not true. 1 cubic meter is not the same thing as 100 cubic centimeters. And remember, when you're doing these dimensional analysis, what you're really saying, like for instance, hours in if I'm converting minutes to seconds, what I would write down is 60 seconds over 1 minute. What that means is that 60 seconds is the same as 1 minute, right? So every time I multiply by one of these, I'm basically multiplying by 1. I'm just changing the unit. I'm not doing anything except changing the unit. So I'm not multiplying by anything but 1. So we call all of these have to equal 1 anytime you multiply. So if you wrote down 1 cubic meter is equal to 100 cubic centimeters, that's not right. Why isn't it?
Because it's cubic.
So
it's 100 cubic.
So yeah, you have to cube the whole thing. That's right. So what that means is if 1 meter over 100 centimeters equals 1, if I want to cube 1 meter, it means I got to cube everything on the bottom. So that would be 1 meter cubed is equal to 100 times 100 times 100 centimeters cubed. You see what I mean? You have to multiply, I have to cube both the centimeters and the 100, both. And so now it's 1 times 10 to the 6th centimeters cubed. So that is a mistake that a lot of people make. So when you do the problem, make sure that you cube the top and the bottom, both the unit and the number in front of the unit. That's really important to do. Let's look at the next problem. Oh yeah, just two more conversions. So again, nanometers. Anyone know how many nanometers there are in a meter?
Negative 10 to the negative 9.
10 to the negative 9 meters. So 10 to the negative 9 meters is equal to 1 nanometer. Or 10 to the 9 nanometers is equal to 1 meter. Either of those. So the way I normally do those is like, I get to a base that I know, like meters or liters or whatever it is, and then go from there. So nanometers, I convert that to meters, and then meters, I convert that to kilometers. Here, 120 pounds per inch squared. You're going to do the same, and you can convert pounds directly to grams if you want, or you can convert pounds to kilograms and then kilograms to grams, either way. But remember, when you're converting 1 inch is equal to 2.4 centimeters, and that's precise actually, that if I square this side, I'm going to square this side too. So I need to square centimeters and square 2.54, both, in order to do that one correctly. All right? And be careful that there's 3 significant figures in 120. It's 120 with the decimal. Always look for the decimal. I think this is just, you're going to need some extra information for this. So what information are you going to need for this question? I want a mass in kilograms. And I'm starting with 16.0 gallons. And I want to get to kilograms. So what do I need to convert?
Density.
I'm given the density.
Okay.
But it's in grams per mil. What the hell's a mil?
We convert the gallons to liters and then use the density to get how many grams in this value.
Right, so gallons, you want to convert that to liters. That's fairly straightforward. But what's a mil? What's an ml?
Millimeter.
Milliliters.
Milliliter.
Milliliter, right. So there
1,000.
is 1,000 milliliters in 1 liter. So you convert gallons to liters, you convert liters to milliliters, and then using the density, you convert milliliters to grams, and then grams back to kilograms. So there's a lot going on in that one. There's like 4 conversions you need to do. Remember to set them up properly, because there's going to be a lot of units in this one. Now, again, you can go directly from gallons to milliliters, but that's a conversion you're really not going to find, because now you have your computers with you to do this, and like for tests and things like that, you're going to be able to look up conversions like this. Usually on a test, I would just give you the conversions, right? I would say there's this many liters in a gallon, and then let you get on with it. You'd have to figure out the rest. So you can either get the direct conversion. It might be hard to find, but gallons to liters is really, that's a basic one, because they're both measures of volume. And milliliters to liters, those sorts of things we should be able to, in a couple of weeks, that should just be second nature. Milli equals 1,000, kilo equals 1,000. These sort of things should just be stuck in your head, hopefully. Okay.
3.7854.
All right, I'm going to do one of these, then we'll end up. So which one do you want to do? There's mass of aluminum to make a rod. This is basically the same question, length of copper wire, and ball bearings. made from iron.
A question.
Yeah, go ahead.
Does pi mean infinite?
Use as many significant digits as you want.
Okay.
Yeah, this is one of those examples where if you have a calculator that gives pi to 17 significant digits, use them.
Okay.
Because you're going to be limited by the other numbers. You're going to be limited by the radius or the volume, depending on which one you're calculating. Don't be limited by pi.
Okay.
Don't use 3.14. That's not good enough. Use as many as
same thing
as many as you can, and then round down after you've done your calculation. Why don't we just do this one then? This has got a lot going on, so we'll do this one together. So again, when you get a question like this, write down the information that you're given. So I have 10.0 kilograms of iron. And what answer do I want? I want number of ball bearings at the end. So I need to go from kilograms of iron to ball bearings. How the hell am I going to do that? So first thing, I have 10 kilograms of iron ore. I do not have 10 kilograms of iron. I have iron ore. What is iron ore? What does that mean? What is ore?
Means something that contains iron.
Right. It's just basically rocks that have iron in it. That's iron ore. Aluminum ore is rocks with aluminum in it. Ore just means rocks with a particular metal in it. So if it's 47, so this means I have 10 kilograms of rock. And if it's 47% iron, and I can get all the iron recovered when I refine it, what's my mass of iron going to be at the end?
Excuse me?
I have 10 kilograms of rocks with iron in it. 47% of that rock is iron. And I'm said to assume that I recover 100% of the iron from the rock.
You get 4.70 kilograms.
How do you get that number though?
47.0% times 10.0.
Right, so I convert my percent to a real number. I can't multiply by 47%. What does 47% mean? What's the actual meaning of percent? If any of you are French speakers, you would know immediately.
Percent means 100th.
Yeah, it means out of 100. Per means for or out of, and cent is the French word for 100, century. So yeah, so it means 47.0 divided by 100 is really what it means. And so we would just multiply that by 47.0 divided by 100. So the actual amount of iron we have to start with is not 10 kilograms, it's 4.70 kilograms. So that's the amount of iron we have to start with. So how do we go from kilograms to volume? Because we've got to calculate a volume here. How do we get from mass to volume? What is that when we have mass over volume?
Density.
That's density. That's right. Very good. Mass divided by volume is density. So we need the density of iron. So if someone wants to look that up, I have it here, but if someone wants to look it up, it would be nice. What's the density of iron?
Density of iron is 7.874 grams per cubic centimeter.
There you go. So 7.874 grams per cubic centimeter. That is the density of iron. So let's start to put all this stuff together. So I'm going to clear this out, give me some room, and write a little smaller. So I have 4.70 kilograms of iron. The density of iron is 7.874 grams per cubic centimeter. And that is the usual units that are given for density. The reason for that is that a cubic centimeter is also equal to 1 milliliter. And so we usually measure volume in liters or milliliters. And so the density, like for instance, the density of water is exactly 1 gram per cubic centimeter, or 1 gram per milliliter. So that 1 liter of water weighs exactly a kilogram. That's basically where those two numbers come from. So that's why we give density in cubic centimeters. So we need to get from mass to cubic centimeters. First thing we need to do, though, is figure out how many. So if we need to figure out how many ball bearings can be made, we need to figure out what the mass of one ball bearing would be, right? Does that sort of make sense? Because we have a mass, and we need to basically turn that into number of ball bearings. Well, it seems like the easiest way to do, seems like the easiest way to do that would be to figure out, well, how much does what's the mass of one ball bearing? And then we could divide it, right? So what would be the mass of one ball bearing? How are we going to do that? We have our formula right here.
You use the density formula, so D equals mv, because they already give you the diameter.
Right, but first I need a volume. That's the very first. So the density gives me the relationship between the volume, which is on the bottom, and the mass, which is on the top. So I need to calculate a volume. What's the volume of one of these spheres? So what is the volume of one of these spheres?
14.137 millimeters cubed.
Yeah, but millimeters cubed, I don't have a unit for millimeters cubed. I have centimeters cubed. What am I going to do?
Divide by, was it 100?
What I want to do is not use millimeters. That's the simplest.
Okay.
That's the simplest thing to do. I'm not going to use millimeters because since my density is in cubic centimeters, I'm going to use centimeters, right? So how many centimeters are there in 3 millimeters is equal to how many centimeters?
30.0.
No. Which one's bigger, millimeters or centimeters?
You go backwards, so it's like 0.3. I hope that's right.
0.3 centimeters.
Right. Centimeters are bigger. Millimeters are 10 times smaller than centimeters. There's 10 millimeters to 1 centimeter.
So
I've got
0.300
centimeters. Okay. So my calculation is V equals 4 divided by 3 pi 0.300 centimeters.
But this is the diameter, my professor, not the radius. We need the radius, so it's going to be.
You're absolutely right. You're absolutely right. It's the diameter. Duh. So what is the radius is twice that or half that?
Half that.
Half that.
0.15.
You're right. Man, I completely, yeah. So that should be, good call. So what should that be? 0.150, right? Because it's radius, not diameter. I totally missed that. Good catch.
Thank you.
Right. So that's my volume is going to be equal to 4 divided by 3 times pi times 0.150 centimeters cubed. So what is my that gives me the volume of one ball bearing. So what's my volume for one ball bearing?
0.1130973.
So what is 0 point
1130973.
That's probably enough.
Okay. Centimeters cube.
That's probably, yeah, like I say, yeah, keep digits, but probably don't need that many, especially if I have to write them down. If I'm just doing it on the calculator, that's fine. And so what's my unit?
Cubic centimeter.
Right. Now, it's going to be real important to keep track of what my units are, because we got so much going on in this question. We got to make sure we have our units set properly. So I now have the volume of one ball bearing. So what is my mass
times the density
of one ball bearing? Right. I'm going to make sure I have the proper units, though. So what I'm going to do is multiply that by 7.874 grams per cubic centimeter. Now that ensures that I've got my cubic centimeters as a numerator, cubic centimeters as a denominator, and I'm left with grams, which is what I want. I want to be left with grams. So the mass of one ball bearing is how many grams?
How many digits do you need?
As many as you want, because we're not done yet.
Okay. 0.890528.
Yeah, it's probably good. All right, grams. So mass of one ball bearing is that many grams. We have 4.70 kilograms of metal to make those ball bearings. So how do I get to number of ball bearings from that?
Convert it to grams first.
Convert what to grams?
Convert 4.70 kilograms to grams.
Okay,
first.
let's do that. So I want to convert that. So I'm going to put kilograms on the bottom because I want to get rid of kilograms. And I want grams left at the top. So how many grams in a kilogram?
1,000.
That's right. So I know I've got the right unit because my kilograms cancel. I'm left with grams. So I have 4,700 grams. Now I want to convert this, since I'm doing lots of conversions, I want to convert that to number. I want to convert that to a number of ball bearings. So what's my last conversion to do?
Divide.
Don't divide. I never divide anything. Ever. I always multiply.
You want numbers? Well, 40.
I want to take my 4,700 and I want to convert that to a number.
4,700 times 1 over.
One what? Units.
One ball.
Yeah, there you go. So I take my 4,700 grams times one bearing or one ball, divide it over 0.890528 grams. Yes. I always want a thing. I want a unit. I need to have something there when I do a unit conversion, or else I'm not doing a unit conversion. So remember, every time we do one of these unit conversions, it has to equal 1, because we're not changing the number, we're just changing the unit. So we have to multiply by 1. So 1 bearing has to equal whatever I've got here on the bottom. And we did that
I didn't know
calculation.
that a ball or a bearing can be a unit.
Yeah, why not? Because that's the question we're asked. The question we're asked is how many bearings or spheres or whatever it is. So we're asked for a thing. And so our answer has to be a number with a thing on the end, or else, it's remember, a number by itself is meaningless.
Mhm.
So I have to, when I'm converting units, I have to have a unit I'm converting to. So in this instance, I'm converting grams to bearings.
Okay.
So I multiply 4,700 by 1 and divide by point blah, 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 blah. And what's my answer?
5277.767
767 bearings.
bearings.
Okay.
Do we truncate the 767 or?
Not yet. We have to go back and see how many significant digits should we be reporting this answer in. Okay. So how do we do that? We go back to the question, and since we did so many multiplications and division, we didn't do any addition, right? They were all multiplications and division steps. So we should be limited by the least precise number given in all of our information at the beginning. So we've got 3 millimeters, we've got 10 kilograms, and we have 47%. Which one of those has the least number of significant digits?
All of those.
Yeah, they all have the same, which is how many?
3 sig fix.
They all have 3, precisely. So our final answer has to have 3 significant digits in it. So now, so we carry all those digits that may seem unnecessary at the time, but we carry them all the way through till we get to the very end, and then we do our rounding. So we need to take this number and round it to 3 significant digits. So what's our final answer?
It's either truncate the 7.7.
We never truncate. Don't truncate anything. You always round.
Round.
Yeah.
But in that case, you don't have enough what's that? Enough materials to make 5280.
Yes, I see what you mean. Yes, but we're limited in our precision to 3 significant digits.
So 528.
So because of that, because of the limited precision, we actually may be able to make 5,280. Do you see? Because we may be overestimated in either the mass or the diameter or in the percent of iron. Because any one of those may be a little bit more than the number that's given. It could be 3.004. It could be 10.04 kilograms. It could be 47.04 percent iron. Each one of those is a little larger than what we calculated. And so the final answer could very well be 5,280. We can't say that it isn't. But 5,280 is the closest number to the correct, it's the most precise number we can give. Okay. We can't give it, we can't say 5,278. We haven't got the precision for that. We can say 5,280. And we very well may be able to make that many because of the imprecision in the other things we've measured. So just Give the bearings, right?
So never
Number in a
truncate?
unit. No,
Okay.
no. Always round. Yep. Because if you truncate, basically you're wasting information. If you truncate, you're basically we don't want to, if we make a measurement with a certain amount of precision, we don't want to waste that precision. We want to keep it. Okay. And if we truncate it, basically we're just taking all the work we did in getting a number that precise, we're basically just throwing that precision away. And we don't want to waste that effort that we made. And so by rounding, we're not wasting the effort. That's a really good point. But you can see why rounding is a better thing to do than truncating. Okay?
Okay.
Okay, good. So, any other questions before we wrap it up? Are there any other questions about any of the other problems or anything else you have before we go? How many folks do we still have with us? Yeah, still got 26 of us, man.
Including you.
This will drop over time.
Oh,
Believe me.
do we get docked off if we just leave early, even though we finished?
No.
No. Wait. Oh, bro, I'm a clown. Sorry.
No.
Excuse me, Professor. Can you send the sheets and the question by mail because I didn't have access to Canvas yet?
Oh, yes, you don't. Okay. Yeah. Good point. I will. Yeah.
Thank you so much. I appreciate it.
Yeah. I'll send that to everybody who asked for this link this afternoon. I'll send. Yeah. Good point. I will send you the. Yeah, man. Because we didn't really have to do this in the summer.
Someone asked in the chat: is attendance required after the sign-in poll?
No.
Oh.
No.
Thank you so much for the help.
Yeah, no, you can show up whenever. Yeah, I need to make sure I can do that. I need to make sure that if you're there at the beginning, I think there's a record, and again I have to find out. I think there's a record of everybody who was here during the session. I think it's somewhere in the metadata. Let's face it. I mean, we're being tracked from space at all times anyway. So I'm pretty sure it's in there. I just need to ask and find out how to get it. Yeah, because some people are brainiacs. They can show up for 10 minutes, get all the information they need, and then go and do it. So, if you can do that, I'm not going to
Excuse me.
Give you a hard time. Yeah.
All right. Thank you.
If it doesn't say assume all the iron in the ore can be recovered from the refining process, truncate that case?
No.
Okay.
No. Basically, that's just there because if you're refining, let's say if you're refining an ore, and let's say iron ore, so you dig up the rock, you give it to a geologist or a metallurgist, and they grind it up and they find out that there's like 47% of this is iron, because they took it into a lab and they extracted all of the iron from it. Well, when you take it into the factory, you're not doing that same thing in the lab. You're doing it on an industrial scale. It's unlikely you're going to get all of that iron out. You're going to lose some. But we don't know how much you're going to lose. And so for this question, we just assume, well, yeah, you'll get all of it. But usually you're never going to get all of it. Just like you're going to find out when we go into the lab. Well, these are virtual labs, so they will work out. But in the real world, some of the labs we would do is you'd actually synthesize something. One of my favorite labs was you'd take some aluminum foil and you would turn it into a sulfate, and it makes these beautiful crystals if you do it right. But it's impossible to get 100% yield. You can't take all of the aluminum atoms and turn every single one of them into a sulfate. That's not going to happen. Even professionals can't do that. So generally you get 80% yield maybe would be really good, or 70% would be good, but you're never going to get 100% yield in any reaction. It's basically impossible.